In this session, I would like to talk about how to represent numbers. Generally, as a human being, we are comfortable with our 10 fingers. That's why decimal system has been introduced, and we represent our numbers using decimal system. Similarly, we have binary, we have ternary, of course, we have hexadecimal, we have octal. Correct. So these are all the wide variety of formats we have. But question number one: what kind of format is comfortable for your computer? So computers are generally designed such a way that they can understand positive and negative signals. Otherwise, I can say two signals. So that's why. So numbers also to be represented in binary. Any data, not only numbers, should be represented in a binary format. Even characters or any information we are going to represent using, even instructions of the computer also can be represented. Otherwise, should be represented in a binary format. Okay, that is one thing you should understand. Second thing, so how to represent integers, how to represent real numbers, all these things we have to study. So before going to that real implementations of that numbers, representations, that means what kind of representation is comfortable for your computer, that we will see at the end. Before that, we will see general representations like what is binary, what is hexadecimal, what is octal. After that, we end up with the representations which we use for representing the numbers in computer. Okay, so let's begin with general representations first. Number representations. Example, you have a number. Okay, let's say that is a positive numbers. Okay, unsigned numbers. When you have unsigned number, how to represent it in decimal? Very simple. Example, you have a number 23, we write 23. Okay, and we say base 10, and this is exactly equivalent to saying 10 to the power of 1 into 2, first digit, plus 10 to the power of 0 into 3. Okay, so both are same. Similarly, we can write a binary format. Correct. Example, let's say 0 0 1 0 0 1, let's say, and base 2. This is a binary format, right? So that is, so what is the equivalent decimal value for that? If you want to know the conversion, so we have to give the weightages. Okay, so every number system is a weighted model: 2 power 0, 2 power 1, 2 square, 2 cube. If you give weights like this, and if you multiply 2 cube into 1 plus 2 square into 0, you are going to get the decimal version of this binary format: 2 to the power of 1 into 0 plus 2 to the power of 0 into 1. Then it would be 8 plus 0 plus 0 plus 1, 8 plus 1, 9. In that way, we can convert binary to decimal. Okay, similarly, we can represent your numbers in octal also. Example, in octal we will have digits 0 to 7. Okay, example, if you have a digit like 777 in octal, what does it mean? How to convert it into decimal? Same idea. 8 to the power of 2, this is the 8 squares. I can say this position represents 8 square. So 8 square into 7 plus 8 into 7 plus 8 power 0 into 7 is the conversion. This will be decimal value. It would be 64 into 7, whatever it is, plus 56 plus 7. In that way, we can convert any I can say any representation to decimal, right? Similarly, you can have hexadecimal like this: a b c base 16 is equivalent to dash in 10. So the formula is 16 square into a plus 16 into b plus 16 power 0 into c, right? We know that 256 into what is a? A is nothing but what is the value of a? A value 10, right? 256 into 10 plus 16 into b value 11 plus 16 power 0 1 into c digit means 12. So in that way, it would be 256 2560 plus something 176 here plus 12. We have to simplify it. In that way, we can convert from other base to decimal. Now we will see how to convert from decimal to binary, decimal to hexadecimal, decimal to octal. Okay, let us see how to convert decimal to binary. Okay, 256 base 10, I would like to convert to base 2, 239 to base 8, 225 to base 16. Very simple. So for that, take 254 and divide by 2 and identify the remainder every time. Okay, so 2 127 is 254, remainder 0. Then again you repeat this process, divide the remaining number with 2, then you get 263 is 126, remainder 1. In that way, we have to identify remainders first. So 231 is 62, remainder 1, 215 is 30, remainder 1, 2 7 is 14, remainder 1, 2 3 is 6, remainder 1, 2 1 is 2, remainder 1, 2 0 is 0, so this is the last point, remainder 1. In that way, so we end up with this point. So after that, nothing. If you continue also, there will be an infinite loop. 2 zeros are 0, remainder 0, 2 zeros are 0, remainder 0, that's why. So this is unnecessary. So after that, we have to write the numbers from top, bottom to top. So it would be 1 1 1 1 1, 3 plus 3 6 7 ones followed by 0. This is binary. So if you have doubt, then you can convert this back to decimal and we can check it out. Let's try that. So we know that the weightages are, how to convert it into decimal. For that we have to give the weightage for every position. 2 power 0, this is 2 power 1, this is 2 square, 2 cube, 2 power 4, 2 power 5, 2 power 6, 2 power 7, right? 2 power 7 into 1, 128, plus 2 power 6, 64, 2 power 5, 32, plus 8, plus 4, plus 2. If you count it, it would be 192, 224, 232, 240, 242, 128 plus 64, 192, up to here 224, 224 plus 8, we have missed 16 also, right? So it would be 192, 224, 240, 248, 252, 254. Yes, so we got it back. So this conversion is right. So in that way we can convert decimal to binary. Let us see decimal to octal. The procedure is same. This time you have to divide the 239 with 8. Then collect all the reminders. 8 2 is 20, 8 2 is 16, then 7, 79, 8 9 is 72, remainder 7, 8 3 is 24, remainder 5, 8, sorry, here it is 8, 8 0 is 0, then remainder 3. It would be 3 5 7 base 8. If you have doubt, you can cross check. Base 8. So this weightage 8 square, 8 power 1, 8 power 0. 8 square into 3 plus 8 power 1 into 5 plus 8 power 0 into 7. That is what we did here also. The process is same. 64 3s are 192 plus 40 plus 7. 232 plus 7, 239. Perfectly right. In that way we can convert binary decimal to octal. Now we'll see decimal to hexadecimal. Let's take 225 and divide with 16. 16 1 is 16, 6 65, 16 4 is 64, remainder 1, 16 0 is 0, then base is 14, remainder is 14. So 14, to avoid the confusion, whether it is a single digit or 2 digits, because in hexadecimal we have 1 and 4 also. That's why the numbers are in hexadecimal are digits 0 1 2 3 up to 9. Then to avoid the confusion, so we use A rather than 1 0, okay? Then 11, 12, 13, 14, right, up to 15. So 14 is E. So it would be E comma 1, E1. In that way we can convert from decimal to hexadecimal, okay? Now we will see conversion between binary to octal, octal to binary. After that we'll see the conversion between binary to hexa, hexa to binary. Okay, let's say 110 0001 and 1. So how to convert this to octal we will see. This is binary. So the technique is very simple. From left side, for every 3 digits should be grouped like this. So you end up with like this. So 011 is 3, right? 000 0 and 11 you add 0. So 011 is 3. In that way 303 base 8 will be the octal conversion. Now if you want to cross check whether these two are equivalent or not, let us convert both of them to decimal. First of all, for this one it would be like this. How to convert, we know that, right? We have to give the weightages. It would be 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5, 2 power 6, 2 power 7. So 2 power 7, 128 into 1 plus 64 plus, so because remaining things are zeros, I am not writing. 2 power 1 into 1, 2 plus 2 power 0 into 1, 1. So it would be 192, 194, 195. Let us convert 303 into decimal. 8 square into 3 plus 8 power 0 into 3. correct? It would be 64 3 is a 192 plus 1 3 is a 3, 195. Yes, that's why this model works. Finally, we can convert binary to octal with this model. Similarly, we can convert binary to hexadecimal. We will see that. Example, you have 1001, 1100, something 101. How to convert this to hexadecimal we will see. From the left side, take 4 digits and group them. Sorry, you have 3, then take that as a group, because always we can imagine 10 here without losing the definition or without losing the meaning. So if I convert that to hexadecimal, it would be, so 0101, is it not a digit 5 in hexadecimal? Yes, so it would be 5. This is 1110, 842 are the weightages. See, focus on 1110. 2 power 0, 2 power 1, 2 square, 2 cube. 8 plus 2 square and 2 cube. 8 plus 4, 12, 12, 14, right? So 1110 is actually a hexadecimal digit now, 14. Convert the 0100 into separately into hexadecimal digit. That is nothing but 2 power 0, 2 power 1, 2 square, 4, right? But 14 we know that is nothing but E, correct? 4E5. In that way we can convert binary to hexadecimal. One more. 1101, 0111, 1010. Let's convert this group like this. 1, 2, 3. So take each group and convert that separately. So 1010 in hexadecimal, for that you should know the decimal value first of all. 2 power 0, 2 power 1, 2 square, 2 cube. This is 8, this is 4. 8 plus 4, 12. 12 in hexadecimal, C. That is the way we have to convert. So this is now to be converted to one hexadecimal digit, it is 7. Correct? So then this one, 1101, 8 plus 4, 12, 12 plus 1, 13. 13 is nothing but D, correct? So in that way, D7C. 10 is A, remember? 10 means A, 11 means B, 12 means C, 13 means D, in that way. So we can convert binary to hexadecimal. We will see now how to convert octal to hexadecimal and hexadecimal to octal. That will be the final one. Example, I have some hexadecimal value like A, B, C. How to convert this to octal? A, B, C, let's take it as 16. Sir, I don't know the procedure. Let's try to use the procedures whatever we have already. We can convert this to binary, but given a binary sequence, we can convert to octal easily, right? That's why let me do that first. Convert this to binary, that is easy. How to convert this ABC 16 to binary? I will tell you. Because did you remember the grouping? For every 4, for every binary 4 digits, we converted them to hexadecimal. In the same way, we do reverse engineering. What is A? A was A means 10, right? 1010. In that way, convert each digit to binary. B, 8 plus 2, B means 11. That means 1011. Next, C means 12, 1100. This is the binary format of this hexadecimal format. Let's cross check. Whenever you have this kind of thing, how to convert to hexadecimal? This one separate, this one separate, this one separate. If you do that, you get ABC back. That means for this one, if this is a hexadecimal, for this one, this will be the binary. So in that way, we can easily get binary representation for any hexadecimal. Blindly do one thing. Take every digit and convert that to binary pattern, correct? C, binary pattern, B, binary pattern, A, binary pattern. Then group into 333 so that you can get octal, right? This is a way we can convert to octal. So 1004, 111, 7, 0102. Now these are all octal digits. 101, 5. So 5274 is octal. So base 16 is converted to base 2, base 2 is converted to base 8. If you want to cross check, if you want to know again, convert this back to hexadecimal. How to do, I will tell you. Given by octal, how to convert to hexadecimal. What you do is, first of all, convert to binary, then go convert into hexadecimal. That would be good. Okay. So when you convert it to binary, you get this back. When you convert it into hexadecimal, you get it back in that way. So binary to hexadecimal to binary, hexadecimal to octal, octal to hexadecimal, everything we can do. Okay. Now we'll see how to convert fractional numbers which are in decimal to binary. Example, you have 1.25 base 10. How to convert it into binary? Before that, I will tell you one important fact. When you have numbers or digits at right side of point, they also will be having weightages, but in a model like this, 10 power minus 1, 10 power minus 2, so on. That means 1.25 can be written as 1 means 10 to the power of 0 into 1 plus 2 means 10 to the power of minus 1 into 2 plus 5 will be having 10 power minus 2 weightage. Okay. Example, if you have 23.45, that can be written as, see, already this part this means 10 power 0 weightage, this is 10 square 10 power 1 weightage, right? So 10 power 1 into 2 plus 10 to the power of 0 into 3 plus 10 to the power of, sir, what about this one, sir? Yes, I am coming to that point. So 4 is going to get a weightage called 10 power minus 1, 5 is going to get a weightage 10 power minus 2. So that is the way this number system is built. So 10 power minus 1 into 4 plus 10 power minus 2 into 5. Then it would be 2 tens are 20 plus 3 into 1 3 plus 10 power minus 1 means 1 by 10 4 by 10 plus this is 5 by 100. If you simplify it, you get 20 plus the 23 plus 4 by 10, actually we write 0.4, right? Plus 5 by 100 will be 0.05. 0.4 plus 0.05, 0.45. 23 plus 0.45, 23.45. Isn't it in that way? So 23.45 can be perceived, right? This rule will be applicable for binary also. When you have binary number, while conversion you can use this formula. Remember it. Now we'll come to conversion part. How to convert a fractional number to which is in decimal to binary. Take like this 1.25 base 10. So target 1. First of all, we see how to convert 1 into binary. We know that directly it is 1. Right? Done. Keep point as it is. Now we are going to convert 0.25 first of all into binary, and we are going to write here. How to convert 0.25 to binary I will tell you, which is base 10, right? The idea will be like this. So rather than dividing, so this time we are not dividing 0.25 by 2. We multiply 0.25. 0.25 into 2. What is the answer? 0.5. So now here this part is 0, right? Then remember that is 0. Next, take remaining part 0.5. So 0.5 and multiply with 2. 0.5 into 2, 1. Whenever you get 1, then this 1 should be remembered like this. In that way we have to remember always this portion. Now take this part again, 0.0. 0.0 into 2 will be 0.0, right? Then you take 0. Then we can repeat this process. Any number of times you repeat, you are going to get 0.0, then 0, 1, 0, 0, 0, right? Again same thing. We have to take from bottom to top. It would be what? You have to take from top to bottom this time. I'm sorry, top to bottom. When you take top to bottom, you get 0, 1, 0, 0, 0, so on. Okay, these are all meaningless. That means not meaningful. Yeah, we'll see the second one, 3.625 base 10. It's in the same model, 3.625. First convert 3 into binary. We know the procedure. You get 1, 1, correct? Then point. So 0.625 has to be converted to binary. The technique is like this. First of all, multiply every time the number into 2, correct? So you get 0.625 into 2, which is nothing but 1.25. Of course 0, 1.250. So here when you do that, this area or this point is nothing but to be remembered 1. Now remaining thing is what? 0.25. Take 0.25 into 2 again. When you do that, you get 0.5. So this 0 goes here. Then this remaining portion 0.5 will come here. So 0.5 into 2. It would be 0.5 into 2 is 1, correct? That means 1.0. Take this one. And the remaining area is 0, right? Take this 0, 0.0. Then stop it, because any number of times you continue, then you will be getting 0.0 and this remainder will be 0, I can say. So these zeros are useless, otherwise that will not add any weightage to the number. That's why it would be 101 followed by any number of zeros. It's like example, you have 2.3000. second one 2.30, both are same, isn't it? So that's fine. In the fractional part, the non-leading zeros are meaningless, correct? That's a thing. It would be 11.101000, so on. We can ignore these zeros, I want to say. Next, 7.375 base 10. In the same way, let us do that. 7 means triple one point, so remaining part is 0.375. We have to convert this to binary. First step, 0.375 into 2, which is 0.750. So here it is 0.750. 0 is remainder. Remember that 0. Then remaining thing is 0.750 into 2, which is 1.5, correct? 1.5. So remember 1. Next remaining part 0.5. 0.5 into 2, you get 1.0. Remember 1 and take this one 0.0 into 2. 0.0. This is again never ending process, so you get zeros here, so we can ignore that part. So only this part is important. 0 1 1, 0 1 1. Okay, don't ignore this 0, this is important, but this ending zeros are unnecessary. In that way we can convert any number which is in decimal to binary when you have fractional numbers. Understand? Now sometimes what happens, you can't represent with finite number of bits. Example, in decimal I will show. When you have 1 by 3, what is the decimal representation for this one? 0.333333. So how many digits you require to represent 1 by 3? Infinite. Without infinite positions, we can't represent 1 by 3 exactly, right? So in the same way in binary also we have such patterns. I will show that. Example, let's say you have 0.2 base 10. Whatever the way you try, whatever the positions you take, you can't represent it. I will show that. Example, try to convert this into binary. We will see, because this integer part is 0, then in binary also 0. I am converting into binary. The remaining part 0.2, correct? Take 0.2 into 2. 0.2 into 2, 0.4. Then remainder 0. Then 0.4 into 2, 0.8, remainder 0. 0.8 into 2, 1.6, right? So 1 is the remainder. The remaining part 0.6. 0.6 into 2, 1.2. Remainder 1. The remaining part 0.2. See, when 0.2 comes, if you do the process, that will be repeated again. 0.4, right? You get again 0. Then 0.4 into 2, 0.8. You get again 0. 0.8 into 2, you get 1.6. So remainder 1, then 0.6 here. 0.6 means 1.2. So again you get remainder 1, then you get 0.2. See, here and here and here, that process will be repeated. It's a never ending story. Then you get 0.0011, 0011. This 0011 pattern will be repeated again and again. So infinite bits are required here also to represent this 0.2 base 10. That means some of the numbers cannot be represented with finite positions. That you should understand. Like in decimal we have 1 by 3, right? So this is about conversions from your decimal to especially binary when you have fractional numbers. Okay, see this one, 123.456 base 8 equal to dash base 10. Okay, so how to convert? So far we have seen for binary, right? Now we'll see for this octal. Very simple, same idea. The weightages will be like this. It would be 8 square, this is 8 power 1, this is 8 power 0, and this would be 8 power minus 1, 8 power minus 2, 8 power minus 3, in that way. So this will be extended to any number of digits. Then if I convert, it would become 64 into 1 plus 8 into 2 plus 8 power 0, 1 into 3 plus 4 by 8 plus 5 by 8 square plus 6 by 8 power 3. In that way we have to simplify. Then if you simplify it, you get decimal, right? Second thing, if you have octal, how to convert it into binary? Example, let's say you have something 0.777. When you have 0.777 in octal, Okay, what I would like to tell you is it is equivalent to 0.11111111 base 2. These two are equivalent. So from now onwards, why it is equivalent we'll see with some example. But before that, you see how to convert binary to octal, especially these decimal numbers are fractional numbers. See, take from right side, take each and every three and convert them to octal. So triple one is 7, triple one is 7, triple one is 7. That's why it is equivalent to 0.777 octal. Okay. So why these two are equivalent? If you want to know, then you should know the simplification process. See, what I can do is, first of all, try to convert this to decimal. So you will understand everything. If I convert it into decimal, so 7 means 7 by 8, correct? So this would be 7 by 8 square. This would be 7 by 8 cube. This is the way we convert this octal to decimal, right? Try to convert this to decimal. It would be, first of all, I am converting this area. It would be 1 by 2 plus 1 by 2 square plus 1 by 2 cube, right? Then this would be 1 by 2 to the power of 4 plus 1 by 2 to the power of 5 plus 1 by 2 to the power of 6, correct? Plus 1 by 2 to the power of 7 plus 1 by 2 power 8 plus 1 by 2 power 9. Why these two are equivalent? We are going to see. Let us focus on this area. So here what I am doing is, because we need 8, right? I will take 1 by 2 cube common in this first component. Then you get what? If I take 1 by 2 cube common, here you get 4 plus here you get 2, here you get 1. Right, now try to understand. 1 by 2 cube into 4 plus 2 plus 1, which is nothing but 7. That is the binary octal equivalent of 111. Similarly here, if you have this area, this can be represented as 1 by 2 power 6. I take common this time, then it would be same story. 1 by 2 power 6, if I take common here, you get 1 by 2 square into 1, 4. Try to understand. 4 by 2 power 6, just take it out. 4 by 2 power 6 is 2 square by 2 power 6, which is nothing but 1 by 2 power 4, right? So that's why 1 by 2 power 4 is nothing but 4 by 2 power 6, plus this would be 2 by 2 power 6 plus this would be 1 by 2 power 6 as it is. So again you have 4 plus 2 plus 1, right? So next time if I take 1 by 2 to the power of 9 common here, you get here again 4 plus 2 plus 1. So in this process you understand finally it is nothing but, this binary representation is nothing but 1 by 2 cube into 111's value plus 1 by 2 power 6 into this binary value in the octal form, and 1 by 2 power 9 into this 4 plus 2 plus 1 in octal form. That means, so 1 by 2 cube into this weightage 111. What is the value of 111? 7. So what is the value of this 111? 7. So what is the value of this one? 7. It is like 7 into 1 by 2 cube plus 7 into 1 by 2 power 6, which is nothing but 8 square, 64. This is 8. So here this would be 1 by 8 cube, 512 into 7. See, 1 by 8 into 7 plus 1 by 8 square into 7 plus 1 by 8 cube into 7 equivalent, right? So this is what happens actually. That's why these two values are equivalent. From now onwards we remember them blindly. That of course with some general variables I can prove, but that is not really required. That's why I did not do that. I am just explaining you the reasoning behind why these two are equivalent. Okay, from now onwards whenever you have something 0 point anything 5 2 4 3 in octal, and if you want to convert it into binary, simply do this process. That's why 0.5, this 5 is octal digit, should be converted to binary 101. 2 is nothing but 010, 4 100, 3 0111. So these two are equivalent, whatever these two, in that way. So from octal to binary, binary to octal we can convert. Similarly we can convert from octal to hexadecimal, hexadecimal to binary. Everything we can do now with this one. So finally we have understood how to represent all unsigned numbers, correct? Whatever it is, unsigned numbers can be classified into two parts, some in integers, okay, positive integers of course, and of course non-negative integers otherwise. So we already see non-negative integer representation, then after that fractions, correct, how to represent fractions in unsigned. Okay, so let me remove this non-negative. Unsigned means there is no negative values, right, automatically. So unsigned integers we have seen, unsigned fractions we have seen, and various conversions from one base to another base we have seen. Now you know how to convert from each base to another base, correct? Yes. Now we will be seeing how to represent negative numbers. So far we have seen positive numbers, correct, and 0. Now how to represent negative numbers? For that we say that how to represent signed numbers. When you have sign, then how to represent them.